Hi everyone! Today let's talk about section 3.3, Reduced Row-Echelon Matrices. The results of the process of Gaussian elimination is not uniquely determined. That is, two different sequences of elementary row operations, both starting with the same matrix A, may yield two different echelon matrices. Each still row equivalent to A, but they're not the same matrix. For example, the two echelon matrices, these two matrices, they are row equivalent. Okay? In the case of a unit solution, it seems that we should be able to continue with elementary row operations until we arrive at the form. So this is the form, and then we can read off the solutions. Remember, the first row is the coefficient of x1, second row the coefficient of x2, and the third row are coefficient of x3, and then this is the right hand side. So that's why the last row we get x3 equals c, and second row x2 equals to b, first row x1 equals to a. So we can read off the solution. We get the x vector is abc. And then the left side, this matrix is called the identity matrix. So the identity matrix, we have 1 on the diagonal. So this is the diagonal. Okay? And then all the other entries are zeros. And so it turns out that these two matrices, they are both row equivalent to the identity matrix. Okay? Which is one diagonal, the other entries are zeros. So in general, we can continue with elementary row operations until we arrive at the reduced echelon matrix, which is unique. So echelon matrices are not unique, but the reduced echelon matrix is unique. So do you still remember what is echelon matrix? Let's see. This is our note of last session. What is echelon matrix? Echelon matrix satisfy those two properties. Every row of E that consists of entirely of zeros lies beneath every row that contains a non-zero element. And then in each row of E that contains a zero element, the first non-zero element lies strictly to the right of the first non-zero element in the preceding row, if there is a preceding row. So this tells us we have a stair shape, okay? And besides those two properties, for reduced echelon matrix, we need each leading entry is 1. And we need each leading entry is the only non-zero element in its column. Okay, so what does that mean? Alright, so let me give you an example. So 1, 2, 3, 4, 0, 1, 0, 5, 0, 0, 2, 6. Okay, so this guy is echelon matrix. Okay, so this is an echelon matrix. But this is not a reduced echelon matrix because you can see the leading entries. This leading entries is 2, it's not 1. Okay, and how do we get to the reduced echelon matrix? Well, you can see we can divide it by 2 for the first row. Then we get 1, 2, 3, 4, 0, 1, 0, 5, 0, 0, 1, 3. And then what happened? We can use this 1 to queue this entry. We can use this 1 to queue this entry. So how do we do it? We can use -3 row 3 add to row 1. And now what happened? So 3 minus 3 is 0. Okay? And then 4 minus 9 is -5. Okay, and then we can also use this entry to queue the entries above it. So we can do minus 2R2 plus R1. We get 1, 0. And now let's copy it on the third row and the second row. Okay, so 2 minus 2 is 0, 0 minus 0, 0, minus 5, minus 2 times 5. Minus 5 minus 10 is minus 15. So now this guy, this is a reduced echelon matrix. Okay, so we can see this is the identity matrix and this is the solution, okay, of the linear systems. All right. So now you can see the leading entries, they are these ones, and the leading entries is the only non-zero element in that column. So look at the first column. This one is the only non-zero entry. Second column, this one is the only non-zero entry. And the third column, this one is the only non-zero entry. So this matrix is reduced echelon matrix. Reduced echelon matrix is unique. Okay? And the echelon matrix are not unique. Okay, so today what we're going to do is we're going to revisit the examples that we did last session, and we're going to continue to get the reduced echelon form. So let's look at this first problem. So this example 1 corresponds to the example 2 of our last session. Let's look at our notes for last session. Okay, so this is the example 2. You see, it's the same problem, right? Okay, so let's see. Okay, let's copy this guy. So let's copy this echelon. So this is echelon matrix. Let's copy it right here. Alright, so we're gonna continue to get a reduced echelon matrix. So do you remember last session when we do the Gaussian elimination, we try to avoid fractions, right? But once you get to the echelon matrix, when you want to get the reduced echelon matrix, it's kind of hard to avoid fractions. So yes, we have to have fractions in some cases. All right, so let's see. Okay, so what do we do now? We want to make this entry to be 1. Okay, so make this to be 1. And then what do? We can do 1/3 of 3. Okay, and then let's see what happened. The first row stay the same. And second row stay the same. Last row divided by 3, and then so we get 1. This we get minus 1/3. Okay, and then next, what happened? We can use this entry to kill the entries above it. How? Alright. How do we get rid of this minus 2? We can use 2 row 3 add to row 2. How do we get rid of this 2? We can use negative 2 R3 plus R1. Okay, now let's see. Because these two are 0, so that's why we have the same. So 1, 0. And then 2 minus 2 is 0. And then 2 minus 2 times negative 1/3. It's the same as 2 plus 2/3. So 2 plus 2/3 is 8/3. Okay? And then next one, we have 0, 1. And then minus 2 plus 2 is 0. Negative 1 plus 2 times negative 1/3. So it's like minus 1 minus 2/3, which is minus 5/3. And the last row stay the same. Now, do you see what happened? This is reduced echelon form. And if you can remember, this is the identity matrix, and this is exactly our solution. See? Our solution here. This is our solution. And you can see they are the same. Okay? So this is reduced echelon form. And you can see it's unique. Alright, let's do more example. So example 2, this corresponds to the example 3 of our last session. And let's see example 3 here. And what is the reduced echelon? The echelon form is this guy. So let me copy it. Okay, so this is the echelon form. Let's continue to make it as a reduced echelon form. Alright, so how do we make the reduced echelon form? We go backwards. We look at the last row. We want to make the leading entry to be 1. So how do we make this guy 1? We use minus row 3. And then we get 0, 0, 0, 1 to be the last row. Okay? And then next, we can use this guy to queue the entries above it, right? So, well, what can we do here? Well, because all these guys are zeros, it won't change the first 3 columns, right? So, but the just last column will change. How do we get rid of this one? We can use minus R3 add to R1. How do we get rid of the 3? Minus 3R3 plus R2. And then we can get 1, 1, 1, 0, 0, 1, 3, 0, 0, 0, 0, 1. Okay, now you can see these are the leading entries. And you can see this leading entry is the only non-zero entry in that column. And then, but we still need to get rid of this guy, right? The third column, you can see there is no leading entry, so it's okay, just leave it as it is. Alright, but we want to kill this guy. This is the 1, 2 entry. Right, so we can use minus row 2 add to row 1 to kill that. Then we have the second row stay the same, last row stay the same. And then 1 minus 0 is 1. 1 minus 1, 0. 1 minus 3 is negative 2. 0 minus 0, 0. Okay, so this is the reduced echelon form. And you can see the leading entries are 1, and they are the only non-zero entries in that column. Okay, and okay, while looking at this reduced echelon form, if you try to solve the system, you can see the last row corresponds to, so the last row we have 0x1, 0x2, 0x3 equals to right hand side. So the last row tells us that 0 equals to 1. And this is impossible. So you can see we still have no solution. Okay, but actually you can get no solution from the echelon form. You don't have to get to the reduced echelon form. So in many of our cases, when we solve linear systems, as long as we get the echelon form, we can do back substitution and solve the system. We don't have to get reduced echelon form. Okay, let's continue. So this example 3 corresponds to example 4 of our last session. Right? Okay, so let's see. choose this. Okay, and copy it, paste. Alright, so let's see. Let me erase this unnecessary things. Okay. Oh, you know what happened? The leading entries, these are the two leading entries. The third row has no leading entry. And the first column, that leading entry is the only non-zero entry in that column. The second column also, that leading entry is the only non-zero entry in that column. So this guy is already a reduced echelon form. So this is the reduced echelon form. Okay, so no work need to show here. And you can also see the last row tells us 0 equal to 0, which is always the case. So we can have infinitely many solutions. And if you want to express them in terms of the parameters, so you just do like what we did before. You can see the third column has no leading entry, so x3 is free. So we can let x3 be t, and then we can express x2 and x1 in terms of t. So we get a one parameter family. Okay, so let's come back. All right, example 4. Given the linear system has a unit solution, what is the reduced echelon matrix? Well, okay, so please pause this video and try to find the answer for it. Are you ready? Did you solve the system? Actually, we don't need to, because if we know it has a unit solution, then what happened? We must know that the system looks like the identity matrix adjoint with the solution, right? So the identity matrix, we put 1 on the diagonal, so the outer entries are 0, adjoint with the solution 3, minus 2, and 4. So this is the reduced echelon form. Okay, reduced echelon matrix. So far, so good, everyone. Okay, let's continue. So, summary. The linear system AX equals to B has one solution, or no solution, or infinitely many solutions. So we call that there are m linear equations and n unknowns. Now let's talk about, because the previous examples we did we have 3 equations and 3 unknowns, so it's like 3 planes in space. Now if we change the number of equations and change the number of unknown, let's see what happened. Okay, so first of all, let's look at what happened if the number m is greater than n. So it means the number of equations is greater than the number of unknown. Well, let's think about some example. What does that mean? Okay, so for example, we can pick m to be 3, pick n to be 2, n to be 2, so we have x1 and x2, so we are in R2, xy plane, right? So then 3 equations, so it's like 3 lines in R2. Okay, now what are the pictures? Well, can we have one solution? Yeah, if 3 lines look like this, then we have one solution. Can we have no solution? Of course, we can have something like this, or something like this, right? Then we have, so this picture, we have one solution. These 2 pictures, we have no solution. And can we have infinitely many solutions? Yeah, we can have all 3 lines are the same line. And we have infinitely many solutions. Okay, so Yes, so it says if m is greater than n, usually no solution, but not always, because we could have other possibilities. Okay. So in general, usually they could be something like this. Okay. For example, look at this guy. And let's write down the arithmetic coefficient matrix. So we have 1, 1, 1, 1, minus 1, 5, 2, 3, 1. Okay, so let's see. We can use this one to cue the entry below it. So we can use minus R1 add to R2. 1 minus 1, 0. Minus 1 is minus 2. 5 minus 1 is 4. And then we can use negative 2 R1 add to R3. 2 minus 2, 0. 3 minus 2, 1. And then 1 minus 2, negative 1. Okay, everyone? And then what happened? Well, we want to make this entry 1. We can swap them. Then we have 1, 1, 1, 0, 1 minus 1, 0, minus 2, 4. Now we can use this to cue the entry below it. Now we get 2R2 plus R3. Then we have 2 minus 2 is 0. And then negative 2 plus 4 is 2. So this is what we get. Oh, can you see what happened? Look at the last row. Okay, remember the first column, their coefficient of x1, and then second column, they are coefficient of x2, and then the last column corresponds to the right-hand side of the linear system. So the last row tells us that 0 equals to 2, which is impossible. So that's why we have no solution. Okay, for this example. Oh, right. So when m less than n, what happened? Well, think about some example. Okay, m less than n. Let's say if m equals to 2, n equals to 3, what happened? Well, n equals 3, then we are in R3, right? Remember, linear equations in R3 corresponds to plane. So this is like two planes in R3. Okay, two planes in R3, they could either intersect like this, or they don't intersect, okay? Or they could be the same plane. Well, these two, they intersect. Do you see? They both have infinitely many solutions. This guy we have one parameter family. This guy we have two parameter family. And here we have no solution. Can we have one solution? No. Two planes we cannot get one solution, right? Think about it. In order to get one solution, you need three planes, right? Or you want to have a surface like that, so you just touch the plane at a point. But because they're plane, you cannot like curve like this, no. So in this case, we can get infinitely many solution or no solution. Okay, let's look at this example. So this example, we can write the arithmetic coefficient matrix. We have 1, 1, 1, 1, 1, minus 1, 1, 3. Okay, use this to cue the entry below it. So we have minus R1 add to R2. 1 minus 1, 0. Minus 1, negative 2. 1 minus 1, 0. 3 minus 1. 2. Okay. Now, do you see what happened? So this is x1, x2, x3, right-hand side. Now, these are the leading coefficients. Can you see the third column has no leading entry? So, because it has no leading entry, so x3 is free. So, we let x3 be t, and then from the last row we get minus 2x2 equals to 2. Oh, x2 equals to minus 1. And then from the first row we get x1 equals minus x2 minus x3 plus 1. x2 is minus 1, so minus x2 is 1. x3 is t plus 1. Oh, so we get minus t plus 2. So the solution, x1 is minus t plus 2, x2 is minus 1, x3 is t. So we get a one parameter family. It is a line. So two plane intersects, and then we get a line in this case. Well, when m equals n, if we have the same number of equations and the number of unknown, then we can have all three possibilities. And we already talked about that in the previous sessions, right? Okay, very good. Let's continue. Okay, homogeneous system. So what is a homogeneous system? It is a linear system provided the right-hand sides are all zeros. So you can see the right-hand side, they are all zeros in this case. Okay, and then for the zero vector, we can denote it as 0. And we put an arrow on top of it. So 0 is, so this is the 0 vector. Okay, so this is homogeneous system. Homogeneous systems, it can have one solution or infinitely many solutions. So only two possibilities, either one solution or infinitely many solutions. We cannot have the case no solution. Why is that? Well, because the 0 vector is always a solution, right? So because a times the 0 vector is the 0 vector, so 0 is always a solution, and we call it the trivial solution because it's so trivial, right? Okay. And what happens if m is less than n? Well, think about some example. If m less than n, let's say m equals to 2, n equals 3, then we have what? We have two planes in R3, right? Two planes in R3. And furthermore, because 0 is a solution. So 0 is a solution means the plane, okay? The plane must pass through the origin. Okay, so two planes in R3 and they pass through the origin. Wow, the picture must be like this. So we must have infinitely many solutions. Okay, so if m less than n, then we know there's only one case, infinitely many solutions. So this is an example. All right, so how do we solve this? We want to make the n1 entry to be 1, and you can see, oh, we have a 1 here, so we can swap row 1 and row 3. Then the first one become 1, 1, minus 1, minus 3, 0. And then the second row, 2, 1, minus 3, minus 2, 0. Last row becomes the original first row, so 3, 1, minus 5, minus 1, 0. So now we have this one. We can use it to cue the entries below it. So we get negative 2 row 1 add to row 2, -3, row 1, add to row 3. And then what happened? So we have 1, 1, minus 3, 0. 2, minus 2, 0. 1, minus 2, -1. Minus 3, minus 2 times -1. So it's like minus 3 plus 2, minus 1. Minus 2, minus 2 times -3. So it's like minus 2 plus 6. So 4. And 0 plus 0 is 0. And 3 minus 1, 0. 3 minus 3 is 0. 1 minus 3, -2. -5 minus 3 times -1. So minus 3 plus, minus 5 plus 3 is minus 2. Minus 1 minus 3 times -3. So minus 1 plus a 9, which is 8. And the last one is 0. Well, can you see the last row is a multiple of the second row? So we can use -2 R2 add to R3 to Q it. So we have 0, minus 1, 4, 0. And then we get all zeros. So this is the echelon form. And we know, because the last row 0 equals to 0, we know that there must be infinitely many solutions. And leading entries are these two. So this is x1, x2, x3, x4, and this is the right hand side. Okay, and if the problem asks us to express this infinitely many solution into one parameter family or two parameter family, you can see in this case, well, this column and this column, they don't have leading entry, so they are free. So we can let x3 be S, x4 be T. And then the second row tells us that minus x2 minus x3 plus 4x4 is 0. Well, we can move the x2 to the other side, become negative x3 plus 4x4. x3 is S, x4 is T. And then look at the first row. First row tells us that x1 plus x2 minus x3 minus 3x4 is 0. Well, then x1 equals to negative x2 plus x3 plus 3x4. Well, x2 is negative s plus 4t. x3 is s. x4 is t. So we have s minus 4t plus s plus 3t. Well, we get 2s minus t. Alright, so our answer, x1 is 2s minus t. x2 is minus s plus 4t. x3 is s, x4 is t. So, and we know s and t, they are real numbers. So this is the solution. We get a 2-parameter family. Okay? Do you have the same answer? Okay, but for non-homogeneous systems with fewer equations than unknown, it can have no solution. So for example, in this case, we have 2 equations and 3 unknown, and you can see if we do minus row 1 add to row 2, we get 1, 1, 1, 0, 0, 0, 0, 1. And you can see this is x1, x2, x3. Last row tells us that 0 equals 1. Well, which is not possible. So we have no solution. Okay, so if the number m greater or equal to n, we can have one solution or infinitely many solutions. Okay, and if we have m equals to n, then the homogeneous system has only the trivial solution if and only if A is row equivalent to the identity matrix. Yes, so we can say our linear system has a unique solution if and only if the matrix A is row equivalent to the identity matrix. Okay, so we know that. All right, so this is what we talk about I forgot to, maybe I should draw a picture here. So in this case, for homogeneous system, right? For example, m is 3 and equals to 2. Well, in this case, we have like 3 lines in R2. Well, and we know it must pass through the origin, right? So we can have this picture. It must pass through the origin, or they could be the same line. Then that's why we can have one solution or infinitely many solutions. Okay, so sometimes drawing the picture can help us to understand. All right, so if you have questions, feel free to ask me. Have a nice day. Bye.